Okay.
Great, thanks.
I think
So, yes, our first speaker is Vincent Caudrelier from the University of Leeds, who's going to tell us about integrable boundary conditions, Hamiltonian and ISM perspective. The stage is yours.
Thank you, Costanza, and thank you to all the organizers. Absolute pleasure to be able to, well, see you virtually, and hopefully we'll get the real thing next year. And yes, I'm going to talk about integrable boundary conditions and more precisely the various approaches and perspective on this huge topic within the context of integrable partial differential equations. And my favorite example is the nonlinear Schr&ouml equation, which well, probably most of you know, but has been nicely introduced and looked at yesterday in the talks by Dennis and Peter. I'm not going to do anything as sophisticated as they did. We'll probably brush over ideas. It's working. So the plan is as follows. So before I can go to point 2, which is, as far as I know, 4 different but related perspectives on integrable boundary conditions for integrable PDEs, I need to review a few well-known facts about such partial differential equations, integrable. And one aspect is probably the most well-known in this conference is the one that involves Lax pairs and inverse scattering method, etc., etc. But there's a complementary aspect for which you can view these integrable partial differential equations as Hamiltonian systems, infinite dimensional ones. And there's a beautiful interplay between the 2 aspects. And what I want to get across is that when you try and maintain this beautiful interplay between these 2 aspects within the context of boundary conditions, you think that everything is done, but actually when you start digging, you realize that different perspectives have emerged with time, and connections between those perspectives are not as well established as you would think. And what I'm going to try and explain is what happens when you start digging about the connections on these 4 perspectives. And it turns out that you can find some really interesting phenomena, and that will be part 3, where I will apply some of the ideas that hopefully I will have got across by then to the focusing nonlinear Schr&ouml equation on the half line with a new type of boundary conditions that can actually emit or absorb a soliton, and that's something you wouldn't see, for instance, with the more well-known boundary condition known as the Robin boundary condition. So before I get there, as I said, I'm going to take the NLS as my favorite example all along. Towards the end, I will focus on the focusing case, so it means that this constant here would be -1, but most of 90% of what I'm going to say applies. If you're not interested in solitons, it applies also for the focusing case. And so the well-known results as follows. So as a PDE and as an initial value problem in a certain functional space, so initially it was like a Schwartz space, you use the inverse scattering method, initially introduced for KDV, but for NLS it was generalized by Zakharov and Shabat, who used this auxiliary problem presentation involving a Lax pair UV involving a spectral parameter K, which I've just realized is going to turn into lambda very soon. And parallel to that, well, you can forget about the Lax pair presentation if you like, and you can also view the nonlinear Schr&ouml equation as a Hamiltonian problem, where your equation of motion is given by time evolution of field, is Poisson bracket of this Hamiltonian here on the field. And that gives you the right equation if you impose this Poisson bracket on your space of initial data. So there are 2 viewpoints on integrability which mimic these two facets of the theory. So one central object, depending on your background, you're going to call it monodromy matrix or scattering matrix, but they're the same thing. So the Lax pair approach, the PD approach, you're going to talk about integrability if you can identify an infinite set of conserved quantities. And the Lax pair formulation allows you to do that. You essentially linearize, that's your sketching matrix. It's got a linear time evolution. Just take the trace of this equality, trace of commutator is 0. So that gives you a generating function because you can, for conserved quantities, because you can also show that this S has, at least the terms on the diagonal, has a nice expansion in 1 over lambda. If you more inclined into the Hamiltonian formalism, there's a nice compact formulation produced by Sklyanin, which involves something called the R matrix. If you know what it is, fine. If you don't know, it's not essential. The bottom line is that you've got the exact analog of this property here, but in Hamiltonian formulation. So you have that this generating function also commutes for different values of the spectral parameter, which ensures that these quantities INs, these quantities are in involution, as it's called. And then thanks to that, you can implement an infinite dimensional version of Liouville's theorem. And the beautiful result by Zakharov and Manakov is that the techniques of the inverse scattering method and the objects within the scattering method are exactly what gives you the action angle variables in this formalism. So actually, the same underlying idea, which is the inverse scattering method, gives you a solution method in both formalisms. So the one that we all know, using Yost solutions and scattering matrices, etc. But also, it gives you action angle variables, which means that you can linearize the equations in time and solve in terms of these variables in the Hamiltonian formulation. So that's, oops. So that's probably 2 decades of work summarized. And what about integrable boundary conditions? So what about if you put your system on a segment, on a finite interval, or for our purposes today, let's say on the half line, to start with. So instead of having the problem on the full line with decaying boundary conditions. So Sklyanin introduced a rather systematic proposal to deal with the same interplay, so Lax pair versus Hamiltonian, but when you try and include integrable boundary conditions, and it produced sufficient conditions to construct conserved quantities in that setup as well, from both points of view. So how does that work? So let me illustrate the half-line case, as I say, with decaying boundary conditions at infinity. So in that case, you replace your scattering matrix on the full line by the half-line scattering matrix, which will relate to your solution normalized at infinity to your solution normalized at 0. And equipped with this half-line scattering matrix, Sklyanin says, let me define this quantity. So that's the half-line matrix, some matrix K, we don't know what it is yet, and then the inverse minus lambda of the same half-line scattering matrix. For some matrix K, 2 by 2 here, because all these matrices are 2 by 2. And let me define this quantity. And then it says, from the Lax pair point of view, suppose now that this matrix K satisfies this condition where V is the time Lax matrix, so the Lax matrix that involves the evolution in time for the auxiliary problem. And you note that there's a minus lambda appearing here. So suppose your matrix is like that, then it's an easy calculation involving this equation and what you know from the half-line scattering matrix to show that the quantity that is introduced is conserved in time. It can also be expanded in 1 over lambda just as before, and it produces for you some conserved quantities. I put a little b here to remember it's with boundary, which are not the same as the ones you would get on the line, but they have boundary contributions, boundary terms, which are dictated by what this matrix K is. In particular, you can extract your Hamiltonian and it will have terms, additional terms at the boundary. Okay, so that's the Lax pair point of view. There's no Hamiltonian structure yet. Now imagine you want to also include Hamiltonian picture. And then, so, well, the analog of this relation is a bit more complicated. Again, if you don't know what the R matrix is, it doesn't matter. What this tells you is that you impose a matrix equation, which is quadratic in this matrix K, and R is known. R is a 4x4 matrix. That's a matrix equation, and the game is to try and classify the possible solutions for such matrix K, just like you would try and solve for K here. And so again, it's a sufficient condition in the sense that if you assume that K is like that and you define S as before, then you have the analog of the result you had on the line, but now on the half line, you can show that these quantities, these modified boundary quantities are in involution, which indicates integrability in the sense of Hamiltonian system now. So that's all very nice, but it doesn't tell you about solutions and how to construct solutions. So a little bit after Sklyanin's work, some people devoted their energy to say, okay, now how can we perhaps use the inverse scattering method in a clever way to actually construct solutions when you have integrable boundary conditions? So this was introduced originally by Habibullin, I think, presented an idea and very quickly developed by a lot of people, the earlier people with Bibikov, and Tarasov. And I think it's actually Gino who coined this name, which I like very much. It's a nonlinear mirror image method. Didn't have this name at the beginning. And what's the idea? Well, the idea is to take advantage of the integrability at the boundary to map your initial boundary value problem on the half line to an initial value problem, which is for which you can use the inverse scattering method. But obviously now the initial data is going to have certain properties. So it's not just any initial data that's going to satisfy the boundary conditions you're interested in. So of all the possible initial data, the idea is to select those that will automatically satisfy your boundary conditions, just like if you select an even function, or let's say an odd function, it automatically satisfies a Dirichlet boundary condition. So that's the same idea, but in the nonlinear realm. And because this idea was very well known for linear PDEs and involves the idea of superposition of solutions, the idea is to say, well, we need something that can execute a nonlinear superposition of solutions. But again, there's a machinery that allows you to do that, and it's the machinery of double Backlund transformations, which I write synthetically like this. So this would be an eigenfunction of the auxiliary problem before transformation, and that's the new one. And L is the matrix that realizes the transformation. And so that would be like a double matrix, and at the level of the potential that realizes a Backlund transformation. But I will probably use Backlund's terminology more often from now on. But I'm sure you all know what I mean. And another solution method that emerged more recently, so that was the early 90s, and this one was probably second half of the 90s, is what's called unified transform or Fokas method. And here the idea is not to try and map your initial value, your initial boundary value problem to an initial value problem, but just to study it in its own right. And this requires the analysis of both parts of the Lax pair simultaneously. So if I summarize, before I summarize, I need to tell you a little bit more about how the solution methods work, because it's going to be useful later on. So the main observation of Habibullin and Tarasov, etc., is that if you consider the equation that the Backlund matrix has to satisfy in X, so that's the old Lax matrix, that's the new one, then the main observation is that if you impose this following condition, so if you impose that the Backlund transformed potential is minus U minus X, that selects for you those potentials I was telling you that are going to satisfy the boundary conditions automatically. So that's the idea. So of all the possible potentials that you could imagine, you select those ones, and then you can show that automatically when you specify the value of L appropriately at 0, you have that U satisfies the Robin boundary condition. So theta is a real parameter here, which appears in the value of L at X equals 0. Now, this backward matrix also satisfies an equation in time involving the time Lax matrices. And from our point of view, so the main message is that this is the key equation for the rest, because if you now implement the following condition, you can relate v tilde to v. It's actually v of minus x minus lambda. And when you evaluate at 0, you get this equation, which for Robin boundary conditions, taking into account that this matrix is constant, that goes away. So that's just Sklyanin's condition if I make the identification that L is the matrix K, which is exactly the case here. When you take this choice, it turns out that this is exactly, oops, sorry, the matrix K that Sklyanin produced originally for NLS. So everything works. But you see, if I anticipate a little bit, you could say, well, Robin boundary conditions are very special. Why would I have necessarily that the value of L, at x equals 0 is constant? Maybe it's a time-dependent matrix. And that's exactly what's going to happen when you investigate a little bit more the connections between all the perspectives I was telling you about. So to conclude with a bit of a pictures, the idea is that this special condition on your potential can be completely characterized by symmetries on the scattering data, because the potential is one-to-one with the scattering data. And in particular, let me give you an example. So if lambda 0 is a 0 of the scattering data, so discrete eigenvalue, then necessarily, if you look at the corresponding symmetry, it tells you that minus lambda 0 star is also has to be a 0. But what this relation tells you, if you remember that the real part is the velocity and the imaginary part is the amplitude, it tells you that for each soliton on one half line, you're going to have another soliton, mirror soliton, with minus the velocity, but the same amplitude. And that's how effectively you can construct a solution on the half line, which looks like it's reflected from actually a 2-soliton solution on the full line with very, very specific parameters. So there's also a symmetry between the norming constant, which controls the phase shift and the position shift in such a way that your boundary condition is exactly satisfied at x equals 0. Sorry. So to finish on the solution methods and to try and paint the connection between all these approaches, within the Fokas method, there's a special class of boundary conditions which are called linearizable. And they're called like that because they can be used to eliminate part of the scattering data which is related to the boundary conditions in favor only of the scattering data related to the initial condition. So it sort of eliminates some of the unknowns in the problem if you have such conditions. But if we look closely about at what the definition is of such linearizable boundary conditions, so well, they're going to be boundary conditions such that you can find a constant matrix n and an invariant function of the linearized dispersion relation. So that's just a function of the spectral parameter that leaves your dispersion relation invariant, such that this holds. So that's the definition taken for linearizable boundary conditions. But for NLS, turns out that this function is just minus lambda. And obviously, this condition boils down to Sklyanin's condition with the obvious identification that n is k. So that's the link between the two pictures in that case. So if I summarize what I said so far, there were, to my knowledge, there are 4 perspectives on integrable boundary conditions. So the original 2 proposed by Sklyanin, which are structural in the sense that they don't tell you much about a solution procedure, but they tell you when things are going to be integrable in the sense of finding infinite number of constants of motion. And then you have a first solution method, which is the nonlinear mirror image method, and another solution method, the Fokas method. So before we started to dig in a few years back, I think that hopefully that's a fair representation of the status of the various topics. let me start, for instance, well, with the easy one, so the one I mentioned more recently. So if you look at the linearizable boundary condition within the Fokas method, that's just what Sklyanin proposed with the obvious identification here. This connection between the nonlinear mirror image method and Sklyanin's equation is via this equation. So you impose that the value of your background transformation at x equals 0 is equal to the reflection matrix. And in the Robin case, this is a constant matrix independent of time. And more recently, I was also wondering, well, what's the connection between the Fokas method with linearizable boundary conditions and the nonlinear mirror image method? And this was done by Gino, Fokas, and Chabelsky, where they established using Riemann-Hilbert problem tools this correspondence. But now the big one is, okay, when we started to dig, quite paradoxically, if you look at Sklyanin's paper and you try to relate the two, you encounter a problem. What's the problem? The problem is that on the one hand, if you try and find the solution for K, knowing V for NLS, it predicts the Robin solution. So it predicts a diagonal constant solution with just one parameter. On the other hand, if you look at the reflection equation, which is the other approach that's being proposed, it predicts something more. It predicts something with off-diagonal parameters for the matrix in front of lambda. So A can be scaled away, say, so you would have your sigma 3 there, but you still have these parameters. For NLS, you have a reduction, which will tell you that C is related to B star. So you still have two real parameters in the game instead of just one. So we're like, well, how could we even resolve this discrepancy of predicting different solutions within Sklyanin's paper? So we resolved this apparent problem, and it leads to interesting consequences. And let me show you the consequences. So if you skip a lot of quite a few years of steps, and the way to resolve this discrepancy is actually to allow a time-dependent generalization of Sklyanin's equation. So if you put that to 0, that's just Sklyanin case. But if you want to understand this new solution for K properly, you need to allow for a time-dependent K matrix, which leads to these boundary conditions with two parameters alpha and beta here. And now the correct generalization of the first connection I mentioned is still that the background matrix at x equals 0 should be equal to the reflection matrix, but now they can be time dependent. And in fact, for this example, you have a solution which is much more complicated than the Robin case, which involves the value of the solution at x equals 0, but it's time dependent. You've got time dependent part here. So now, what's the status of all these connections after these results? So now we understand. That was the part we didn't understand before. Now we understand it, and you have to allow for this generalization. But now we've understood this. This creates actually new open problems. The first one that's I want to present quickly is now what's the new connection between how do you implement the nonlinear mirror image method in this case for these more general boundary conditions? And then a completely open problem is, well, what is the notion of time-dependent linearizable boundary conditions? That should also appear in the Fokas method. And then how do you relate these two? So now I'm going to concentrate on this connection. And to appreciate the results, I'm just going to flash the way you understand how you can have Robin boundary conditions and construct solutions for Robin boundary conditions. The best way is to characterize, as I said, those specific potentials by symmetries on their scattering data. So before I only mentioned the symmetry on the eigenvalues, but obviously there's a symmetry on the corresponding norming constants. So it tells you that the two solitons that meet at the boundary have to do so in a special manner. And there's also some symmetries on the continuous data if you have more than just pure soliton solutions. So that's the Robin case, well understood and well studied. And now I'm going to skip that and show you the results for the new boundary conditions. And actually, you have two possibilities. Case A is very similar in structure to the Robin case. So this is exactly the relation we have for Robin case. This is very much the relation we had between B for the Robin case, except this function is different and now incorporates the two boundary parameters, but in complete analogy with this relation here, which came from having the Robin boundary conditions with one parameter, gamma, which is related to theta. And the norm, similarly, the norming constants, if you have zeros, are also related in a special way, which is controlled again by this function to the right zeros. So in structure, almost nothing new compared to Robin, except for this different symmetry function. You also have pairs of associated zeros and self-symmetric zeros, which means zeros that have this property, but because they are purely imaginary, they're just on their own. One difference with Robin is that this number is necessarily even in that case. And now comes the new one. So that's something you wouldn't see in the Robin case. You see that now this function is carried by A, not B, which means that A has necessarily a zero involving the parameters of the boundary. And also there's something a bit different happening with the norming constants. That's the new feature. And if you plot, so that's the equations, if you want, and if you plot the results, in case A, you would have what you would expect also for Robin. So that's, for instance, a two soliton solution being reflected. So you have your soliton interacts with the other one, it's reflected, and the second one like that. And here you have your boundary condition being that holds. And the difference between the two is just you shift the position. And that's something you would get without with Robin as well. Now the new case, very different. So there is a possibility of having one soliton reflected and one absorbed. And if I shift the parameters a little bit, I can also push that one up a little bit, and then you have the other scenario where this one is reflected before this one is absorbed. So that's the takeaway, if you like. So by trying to look to unify all the various perspectives that were known for integrable boundary conditions, if you start digging a little bit from in the Hamiltonian aspect, you can actually bring back information, and when you try to implement it from the point of view of partial differential equations, you stumble upon this phenomenon. So actually, we only realized that 2 weeks ago. So quite excited, but there's a lot to understand. Let me skip that because of time. Go back to that questions. So yeah, the summary is exactly what I've said. So by trying to understand Sklyanin's original paper and the two approaches, Hamiltonian and Lax, we realized that you needed to go beyond what was well known and established for analysts. So you need to go beyond the Robin boundary conditions. And then when you try to implement a nonlinear mirror image for that, you come up with this new feature that a very particularly tuned soliton, whose parameters are tuned to the parameters of the boundary, will be either absorbed or emitted. That's something you wouldn't see in Robin. Lots of open questions. So far, we've only looked at that for what's called generic potentials. So things, with finite number of simple zeros. But for instance, yesterday there were very nice talks about all sorts of more complicated or exotic solutions, and could we have more exotic phenomenon of absorption and emitted solitons for these solutions? One big question is, what's the time-dependent version of the linearizable boundary conditions within the Fokas method? And one last question, and I'll finish on that, which is dear to me, but perhaps beyond the scope of this workshop, is this picture is well known to have connections with the quantum reflection equation. These pictures, classically, I had never seen them before, but quantum mechanically, they suggest some connection with what's called reflection transmission Young-Baxter equations. So there's been some activity about finding set theoretical solutions of the Young-Baxter equation and the reflection equation in those papers. So would it be the case that we can find set theoretical solutions of these equations by looking at multi-component solitons? And probably many other questions that we can imagine. And I'll finish with just some selection of references. Thank you for your attention.
Thank you very much, Vincent, for your very nice talk. Are there any questions? So there is a question from Sylvie in the chat, if I manage to open it. Oh, wait a sec, that's not opening for me for some reason. Okay, so Sylvie is asking, have you thought about these questions for other integrable PDEs?
Yes and no. So as I said, obviously I thought about it, but this very nice part, this very last part that I mentioned about this specific phenomenon, we just realized it for NLS a couple of weeks ago. And even though we actually implemented this same idea for Ablowitz-Ladik, so the discretized version of so not the partial, a discrete version, half discrete version. It looks now in hindsight that we may have missed this phenomenon in that, but it should be there. Now, I suspect Saint-Gordon, you'd have to carry out an analysis along the same line. So I'm not saying it's easy, there's a lot of steps, but in principle, it's possible. The easiest way, you probably need to start with a PDE that is amenable to the nonlinear mirror image method, so that has an underlying space symmetry, a Z2 space symmetry. So for instance, KDV, if you were to ask about KDV or modified KDV, that's where the question within the Fokas method becomes extremely important, because that was one of the reasons for the Fokas method in the first place, that the nonlinear mirror image method, when you have a PDE with dispersion relation that's cubic, there's no obvious involution. There's no obvious, lambda to minus lambda symmetry. So that's where that's all I've thought about so far. Sorry.
So I see in the chat there is another question from Benjamin, who's asking that, so in integrable QFT, there are some results that suggest a no-go theorem, namely that reflection and transmission are only simultaneously allowed if the theory is trivial, so free. Do you think this does not apply to quantum mechanical systems?
Yes, so I knew Benjamin will ask something like that. We can probably carry it. Of course, that was the topic of my PhD, Benjamin. So when I saw these results 2 weeks ago, I started to have nightmares again. So, okay, it's a big question. I don't know. I think now I need to go back on those questions and with a fresh eye and see. Oh, it's Elijah. Sorry. Hey, Elijah, how are you? Okay, so yeah, of course, you know very well. Yeah, I don't know what's going on. At the moment, I just say, there are these solutions, you put them, you have explicit formulas, put them on a computer, you see that's what's happened. So I guess the first question would be to say, in the quantum field theoretical context, what's the analog of this time-dependent K matrix that we have? So I know, Corrigan and company, they have this, they have done works for what's called dynamical boundary equations. So I don't know, maybe there's something. No, it's fine, it's fine. So yeah, okay, the short answer is I don't know now. It's puzzling what's going on, but exciting at the same time, I think. Already classically, I want to understand what's going on better, and then of course I'll go back to my old passion maybe one day, or we can discuss more about that.
Okay, if there are no other questions, let's thank Vincent again